everyone. Welcome to this session. I'm Sun Li, assistant professor from the Hong Kong University of Science and Technology, and I will be the session chair. Let's first welcome the first speaker, Zijian Zhao, who is from the Hong Kong University of Science and Technology, to give the first talk. Dear Manoj, can you help to play the recorded video? Okay, thank you.
Hello everyone, my name is Zhao Zijian and I'm a PhD student in the Hong Kong University of Science and Technology. Today I'm glad to share our latest work named Discriminatory Algorithms and Payment Setting of On-Demand Food Delivery Platforms, the Impacts of Data Privacy Regulations. Recently, more and more food delivery platforms start to use the learning algorithms like the reinforcement learning for labor management. Compared to conventional model-based method, the learning-based method can take the future uncertainty into consideration, realizing better planning and optimization. However, such black box method leads to the problem of algorithm discrimination. For example, the algorithm may set different payment for carriers with the same work, violating the principle of equal pay for equal work. It may also have different dispatching preference. So in the same time period, different carriers may have very different workload. Such algorithm discrimination actually hurts carriers in both the mental and physical health. Such algorithm discrimination problem can be attributed to the overuse of privacy data of the food delivery platforms. To address this problem, some governments have proposed the data privacy regulation policies, like the GDPR in Europe, the PIPL in China, and the CCPA in California. Such data regulation policy aim to restrict the overuse of data of the food delivery platforms. They allow the carriers to decide whether to allow the platform to use their individual data by themselves. It also allows the order to change their options at any time they want. However, mostly current works are based on statistical analysis and interview survey. So it's still unsure how the algorithms discriminate different carriers and how the DPR influence the behavior and profiles of platform and carriers. So to answer these questions, in this paper, we aim to develop a reinforcement learning framework to model the behavior and strategy of both the platforms and the carriers. However, we actually meet some significant challenges. For example, it's hard to optimize the dispatching strategy and payment strategy jointly of the platform, since the dispatching is a discrete action problem, but the payment setting is a continuous action problem. In the field of reinforcement learning, the joint continuous and the discrete action space optimization get very limited discussed. For the carriers, we need to model their behavior on different timescales. In the long term, they should decide whether to work on the platform and whether to share their personal information. In the short term, they should decide whether to accept the assign orders at every time step. So additionally, the game process is very complex. That there is not only the game between platform and carriers, there is also games among the carriers themselves, since each carrier aims to maximize the profits of himself. Then the research question can be concluded into 3 points. First, how to model and optimize the behavior and strategy of platforms and carriers. Second, how does the discriminatory algorithm influence platforms and carriers? And third, how does data privacy regulation policy influence the food delivery market? And this figure shows the workflow of the food delivery system. At the beginning of each time period, the carriers should take a long-term decision. They should choose from the opt-in, that is working with providing personal information. the opt-out, that is working without providing personal information, and exit, that is not working at this time period. Then the customer can set the order as arbitrary time to the platform. After receiving the order, the platform will assign orders to different carriers with the proposed payment. Then the carriers can decide whether to accept the order according to the information like order distance, the proposed payment, and their own reservation value, which means the expected salary to accept the work. Then if the carrier accepts the order, they will start to deliver it with other en route orders. But if they reject it, then the order will go back to the platform, and the platform will try to reassign this order in the next time step. However, if an order is not confirmed in a time threshold, it will be cancelled by the customer. Then for the platform, we model its behavior as an MDP, the Markov decision process. For the state, we divide the global state into the state of each carrier. For the state of each carrier is consisted by the current time step, the carrier information, including the current location, the remaining capacity, and the en route order informations, and the information of the orders to be assigned at this time, and the global information such as the number of carriers who choose to opt in and opt out. Then let's discuss how the platform records carrier individual information in the state space. The simplest manner is to record all the behavior data related to the accept and reject orders. However, it can lead to a very large data volume, which is unfeasible in practice. Then we propose an alternative approach that we only record the average unit payment of the accepted and reject orders using the exponential moving average method. Then the platform can classify carriers based on this historical behavior data. And for the action paths, each carrier has two actions. The first is the order assignment action, and the other is a payment setting action. For the reward function, the global reward can be read as the summarization of the reward of each carrier. And the reward function of each carrier is consisted by 5 terms. The first 2 terms is the income from customers. The second term is a platform outcome, that is the payment to the carriers. And the last 2 terms is related to the delivery time, which is related to the satisfaction level of carriers. And for the carriers, we use a logic model for short-term decision. Here, the UA and UR represent the utility of accepting and rejecting orders respectively. And the UA is proportional to payment and inversely proportional to the reservation value. For the long-term decision, we model it as a CMAB. For each carrier, they should take the long-term decision according to their own state, including the information of the reservation value, the initial location, and the platform strategy. Then if the carrier chooses to work in the platform corresponding to the opt-in and opt-out action, they will receive the accumulative income over the entire period as the reward. And if they choose exit, then the reward is a fixed utility. Let me introduce the solution method briefly. For the MDP of platform, we use DDQN for order assignment. Here we use a neural network to estimate the Q value of each carrier and order pair. Then we can use the bipattern match to find the optimal dispatching strategy by maximizing the global Q value. Then during training, we use the TD learning method for optimization. Then for the payment setting, we use PPO, which is a very popular reinforcement learning method for continuous action control. And here there is an interesting finding that the PPO, the V value of the PPO is equals to the Q value of the DDQN with the optimal dispatching action. So there is no need to train another critic network for the PPO, and we only need to train the actor using the policy gradient method. Then for the CMAB of carriers, we use the Thompson sampling method. We model the reward of each state and action pair as a Gaussian distribution and use the MLE for optimization. Then during exploration, we can greatly select the action with the highest reward expectation. And during training, we found it's very hard to train the platform strategy and carrier strategy at the same time, because their strategy actually influence each other. So we propose a two-phase training method. In phase one, we set the carrier strategy as a random strategy and train the platform to generate the optimal response to all possible decisions made by carriers. And during this phase, we train the DDQN and the PPO alternatively. Then after the platform strategy is well trained, we fix it and then train the carriers to identify the optimal long-term decision and to maximize the cumulative earnings. Then to validate our method, we conduct the experiment using the real-world dataset, food delivery dataset in Hong Kong, China. We compare the DPR policy with other two policies named the benchmark, where only the opt-in and exit choices are provided, and the mask where is only the opt-out and exit choices are provided. Then these figures illustrate the relationship between the unit payment, total workload, and total earning, and reservation value. Here, the blue lines corresponds to the opt-in carriers in DPR policy, and the red curves corresponds to the opt-out carriers in DPR policy. Here we can notice for the opt-in carriers, the higher reservation carriers can receive higher unit payment, the lower workloads, and they have a lower total earning. But for opt-out carriers, we notice they still have a higher unit payment. Even the platform cannot access any individual information of these opt-out carriers. So this is caused by these high reservation carriers reject the low payment orders by themselves. As a result, they have a slightly lower workload, but in total they have a similar earnings compared to low reservation carriers. Then we can also notice for the high reservation carriers, they can get a higher earning by choosing the opt-out choice rather than the opt-in. And this figure shows the proportion of choices among carriers in different policies. We can notice in the DPR policy, as the reservation value increase, more carriers choose the opt-out rather than the opt-in. This is because they can get a higher earning by the opt-out choice. So in conclusion, the DPR effectively protects the rights of high reservation carriers, allowing them to choose opt-out to access more work opportunities. Additionally, you can also notice that in DPR, there is a lower average exiting rate compared to the benchmark and mask policy. Then let's discuss how the DPR affects the platform profits and the customer satisfaction level. Here we can notice that the DPR can provide a higher profit for the platform compared to the benchmark and mask. This is because in DPR, more carriers are attracted to work in the platform, so the platform has the opportunity to serve more orders. Then it gets a higher profits from the customer. Additionally, the increased amount of active carriers can also help the platform to optimize the order assignment strategy better. So it can lead to a lower delivery time and a lower overtime rate. then the customer can get a better satisfaction level. So in conclusion, the DPR is actually creates a win-win scenario that the carriers, especially the high reservation carriers, can get a higher earning by take the opt-out choice, and the platform can get a higher profits, and the customers can get a better satisfaction level. That's all. Thank you.
Okay, thanks very much for the presentation. Is there any question from the audience? Okay, so if there's no question, maybe I guess we should proceed to the next talk. The second talk will be given by Wissam Kantor from the University of Nebraska-Lincoln.
So my name is Wissam Kantar. I'm a professor at the University of Nebraska-Lincoln. I'm actually going to be presenting based on my student's work, Muhammad Alian. So we're looking at the consensus-aware AV behavior, trade-offs between safety, interaction, and performance. So what are we looking for is the idea that, transportation systems are ever dynamic and ever complex. And specifically now, we all know about mixed traffic, about the human behavior, human-driven vehicles, that they are really problematic and complex to analyze. So when we add AVs to them, we're adding a layer of complexity here. And this layer of complexity is because of those AVs are designed with some algorithmic decision process designed with some control logic in mind. So when we put those AVs in the transportation system, now we have a collision across 3 dimensions. First, we want them to be safe so that they should minimize collisions, they should have a safe operation. And then the other level of complexity is the interaction. So when we put them in interaction with other drivers or pedestrians, then we need to maintain safe, smooth interaction. And then a always mistakenly or overlooked aspect of AVs in traffic is that they should make traffic better, right? We don't want to go back to unstable traffic, traffic jams, traffic buildup. So we really want to improve the performance of the traffic system itself. So here is the idea of this complexity is that, and we've seen some aspects of it, we're going to talk about them in empirical data, that, an AV could be maximally cautious, could be maximally safe, but then it slows down traffic or it even confuses pedestrians, because pedestrians do not understand how these vehicles behave. An AV could be very much efficient in its maneuver, but then it raises the crash risk. And if we analyze some safety surrogate measures as time to collision, TTC, or post-encroachment time, PET, then we see these issues rise up. So the idea here is, and our contribution is, we want to understand consensus. So we want to metricize it, we want to model it across those 3 dimensions that we've discussed. So we define here behavioral consensus as an alignment across safety, and we measure it through time to collision, TTC, PET, post-encroachment time, and conflicts. And then as a measure of interaction, which is how pedestrians behave or hesitate around AVs, and what is their deceleration maneuvering. And then finally, across performance, and that is the performance of the traffic itself. Recently, the interesting idea that there isn't really much empirical data on consensus. So can we empirically verify it or understand it or model it? So what we do here is we use the very recent data set from the 3rd generation simulation data set, TGSIM. It has just been released this January, and it looks something like this. So it's a real-world data set, high resolution, 0.1 seconds. It's collected across 4 urban intersections in Washington, D.C. It includes autonomous vehicles, human-driven vehicles, vulnerable road users, VRUs, buses, scooters, and others. And it mainly focuses on left turning. So it's an urban setting, which is very much useful to us because of the idea of different interaction between different people inside the transportation system. And one of its limitation is that it's only left turning. So this is how it looks like. This is an actual place. It's called Foggy Bottom in Washington, D.C. So it's four intersections connected to each other. And then AV, seen here as a red dot, would traverse those four intersections, doing left turns across all those intersections. So it's like kind of doing a loop across this system. So what did we do here? We extracted the trajectories and we measured different set of measures for every dimension. So then we compared the AV behavior to the human-driven vehicle, referred to as HDV behavior. So we identified the interaction zones. So we identified every time an autonomous vehicle is interacting with other modes of transportation. So if an AV is interacting with human-driven vehicle, with a pedestrian, with a motorcycle, with a truck, we identified all those instances. And we computed those measures, which are time to collision, post-encroachment time, headway, acceleration, deceleration, string stability, and hesitation patterns. We used all those to define consensus regions across time and across space. Let's see some of our, this is basically the study framework. We start from a high resolution data set. We have 3 dimensions of analysis, and then we try to estimate consensus. Let's look at some of our results. We start first with TTC patterns, which is a proxy for safety. AVs maintain higher TTC values, which is interesting because which is suspected because they are generally more reactive and more safe. But the interesting issue is that HTVs spend more time under 3-second TTC. So the 3-second TTC, which can be shown in this right-hand figure, is like a threshold that's typically used to measure the safety critical element of TTC. What's interesting here is that while human vehicles, this is a cumulative curve, while human vehicles spend more time in TTC under 3 seconds, it is often resolved slower than that of HDV. So we can see that the number of frames an autonomous vehicle spends in TTC less than 3 seconds is less than that of a human-driven vehicle. However, it is more frequent, which is kind of interesting. So they are more safe, but there are some of those instances where an AV finds itself in a safety critical situation. We then looked at the PET patterns, which is the post-encroachment time as well. Here we see that AVs generally maintain clearance. There are some few outliers which we take upon this threshold of 2.25 seconds. So we see few amounts of times where there are autonomous vehicles that have a PET less than 2.25 seconds, which is a bit problematic because we really and ideally we want to eliminate all those case scenarios. To understand better this idea of PET as well as in hesitation, let's look at this interesting deceleration plot at the left turning. So directly when you look at something like this, you could directly see that generally more smooth, so autonomous vehicle, which is the figure to the left side here, they are more smooth, their acceleration profile, or here the deceleration profile around maneuvering this intersection is very much smoother than that of human-driven vehicles. Human-driven vehicles tend to accelerate faster and decelerate even harsher. So AVs have smooth braking, they have less variability. HDVs have abrupt and very much reactive deceleration. But the idea here is that what's interesting is that at the at these types of turns, you have pedestrians that can be crossing or available on the crosswalk. So we wanted to understand whether pedestrians feel safe around AVs or not. And we saw some interesting ideas here that when we try to model like how close an AV comes in proximity of a human trying to cross this intersection, we detected some instances that there is hesitation by the human crossing when an AV is present. We measure this hesitation as a factor of speed in the crosswalk as well as a factor of distance to the autonomous vehicle. So what you want to understand here is that typically a human and a human driver, they have cues that they can interchange, which is by looking at each other or by, a human understands kind of the body language of a pedestrian. So they can kind of communicate. But when it comes to AVs, this communication is still not available. So when they are not able to exchange information at this intersection so that there is no hesitation by the human crossing the crossroad. So that's an interesting observation here. We looked at the headways. So we have two kinds of headways here. We have headway as an entry to this intersection. Remember intersection, so it has traffic signals. So as an entry to the intersection, and then finally as a exit to the intersection. So here, what's interesting is that human-driven vehicles, generally a platoon that is led by a human-driven vehicle, they tend to accelerate faster upon leaving the intersection. So when the green light is on, they accelerate faster, which is kind of beneficial from a throughput perspective. But AVs are much more conservative in their behavior. So they leave larger gaps and they exit slowly from an intersection. And we saw this from the acceleration profiles. So this raises some question of, are they causing some delays at an intersection or not? We then measured the string stability. So let me go back here. Remember that we are at an intersection, but those stretches of a road between an intersection and other, they are good stretches of road. So we could measure kind of string stability there from a car following perspective. So what we noticed there is that sometimes AVs, they cause traffic disturbances closer to the crosswalks. So because they tend to break there, their behavior is around the intersection probably a bit unpredictable for human drivers. There are some instances where disturbances can grow from this performance, and they amplify along the intersection region. So this is a bit alarming because we've seen that autonomous vehicles in traffic systems, and specifically in highways and in freeways, we are able to control them in a way to dampen disturbances and to attenuate traffic. But from an urban level perspective, still more research needs to be done on that. Finally, here's a kind of a figure if you want to get, something out from this presentation, is that along all the interaction frames that we've analyzed, all this data set that we've analyzed, we only saw 1.66% of the frames satisfied consensus. So basically meaning 1.66% of the time, an AV managed to be safe, good interaction quality, and improve the traffic performance. So you can see that consensus along those three dimensions is basically very rare. And most of the times an AV fails at least two of those conditions. So, which is an interesting observation here, specifically from an empirical setting, that, AVs, there's like a Pareto optimality here because they are not able to optimize all dimensions of transportation interactions. So at some point, there's something missing. It's either safety, it's either interaction, or it's either performance. Here we also kind of put together an idea of how the trade-off manifests. So, for example, when you value safety, your hesitation interaction quality decreases and your performance can increase. So this is like a kind of a trade-off. There's always something that you're sacrificing at the sake of something else. So key takeaways here, I'll finish by the slide that so AVs definitely behave more conservatively. They are safer around vulnerable road users. However, this issue that their behavior is unclear yet to VR use, so we are seeing some hesitation when those two agents are interacting. HTVs are intuitive, like people know how HTVs drive. We've been analyzing them for so long, and they remain very much heterogeneous, very much variable. And finally, consensus is rare in the real-world interaction. So the idea that we are achieving consensus across 3 dimensions is rare and it's not happening, and we need to focus on that. Finally, there are some limitations. Actually, we have expanded on this work at the time of our submission. We added more data sets and we added different transportation sites. So it's not just urban setting, but we added other geometries and freeways and merging sections and so forth. We expanded on the safety surrogate measures as well, but there remains like those kinds of limitations that we are still working on. In summary, I leave you for those two QR codes. Feel free, I'll drop them in the chat box as well. So the first is our full paper is available on arXiv. You could read through it and see, get more details, as well as we put a full reproducible GitHub repository. There you could basically replicate all the safety metrics that we've analyzed, as well as our kind of process data set that we've put through. So I'll feel free to scan those and I'll drop them as well in the chat box. Please let me know if you have any questions. This is the end of my presentation here.
Okay, thanks very much for the interesting talk. So there's one question from the chat room. Is there any comparison done between human-driven vehicles consensus and AVs in this database?
Yeah, that's a very interesting idea. As well, humans do not have consensus. I don't have a measure for you on the top of my mind. So, for example, this 1.66% of AVs, but we're sure that human-driven vehicles as well do not achieve consensus, and we've known this for so long that they even cause traffic problems. But the idea here is that, so this is interesting because AVs are put in the system because we can control them and we can design them the way we want. So they are put in a system to improve it in many aspects. So this is the idea that if you want to achieve consensus, we want to focus on AVs because this is what we can control. This is what kind of we're introducing in the system. Human-driven vehicles are variable. They have some sort of a known behavior, but to some extent we cannot control them beyond some traffic management level of control. But yeah.
Okay, thanks very much for the answer. And is there any further question from the audience? If not, let's thank again for the wonderful talk, and we will move to the next one. Okay, so the third speaker is Naomi Panjaitan from UC Davis. Please go ahead.
Thank you. Okay, good afternoon. My name is Naomi Panjaitan. I'm a PhD student in Transportation Technology and Policy at UC Davis. It's an honor for me to be able to share my work with you this afternoon. This work I do with my advisor, Dr. Sudhi Pike. It's entitled Exploring the Significance of Care Trips in Daily Mobility. So maybe some of you haven't heard about the term care trips or are not familiar with that, but I believe almost all of us, if not all of us, okay, let's see. Okay, have done at least one of these activities. Like for example, you go shop for your groceries at least once a week, or maybe once a month, or maybe some of you this morning just drop off your kids to summer camp, and then this afternoon you need to drop by the bank to run some errands. Tomorrow is your dentist appointment. So these kinds of activities, we do them on daily basis or weekly basis or monthly basis, and they are part of our daily lives. We do these activities to take care of ourselves, our household members, and our household itself. Because of these activities are distributed spatially, we need to travel to do these activities. And to do these care activities, we call them as care trips. So as the background here, okay. Sorry, it's a bit lagging on my end. Let's see. Okay. So as the background here, I would like to repeat that care trips are trips to take care of our households and household members. And this is derived from the concept of the mobility of care. So the concept of mobility of care acknowledges that travel patterns of men and women are different. And this concept also advances the idea that gender-based differences should be considered in transportation planning and practice, because women are generally more responsible for carrying out care-related activities. But we know that nowadays in our modern life now, care trips are underemphasized in a commute-centric transportation system we have. Although actually, care trips make up a similar proportion of daily travel as work trips. And previous studies also found that gender and children's presence in the household are associated with care trips. Although we don't have a clear reason why women are more involved in care trips and care activities, but one of previous studies found that women are more stressed than men when they travel for care, although actually both men and women value care activities as meaningful activity for them. So because of that, we posed 2 questions. The first one, we would like to know how significant are care trips in people's daily life, especially when we compare care trips with work and leisure trips. And the second question we posed is, for whom are care trips a significant part of their daily activities? To answer these questions, we apply MTCEV choice modeling to a household travel survey data. The household travel survey data we use is 2022 US NHTS, or National Household Travel Survey, which we have more than 6,000 individuals within the age range of 18 to 64. And the choice modeling we use here is multiple discrete continuous extreme value. What is unique about this method from the traditional or conventional MNL or multinomial logic model is that in MTCEV, we take account dependent variable that have 2 elements, which is the discrete element and the continuous element. And in our case, our dependent variable is the travel time related to the trip type. So the discrete element of our dependent variable is the trip type, and the continuous element related to that is the travel time to do the trip in minutes. So to further elaborate how we do our analysis, here I lay out the conceptual model, how we apply MDCEV to NHTS. So we would like to see how the independent variables affecting the dependent variable. Our independent variables are the sociodemographics. We took a look at gender and then children's presence, and then the interaction between gender and children's presence, and also the household incomes. We would like to see how they affect people time allocation to different types of trips. So the time use we put here is in minutes, and the alternatives we have in our models are activities that people take throughout 24 hours they have. So we have all non-travel activities, and this counts as outside good in MDCEV terms. So this outside good or all non-travel activities is the alternative that all observations or individuals in the model take. So all the observations, of course, do all non-travel activities. And then we have other alternatives, which are the trips. We have homebound trips, care trips, work trips, leisure trips, school trips, and other trips. But we will focus more on three main categories we have, which are care trips, work trips, and leisure trips. And how do we divide these trips, the trip purpose, into these categories? So on the right-hand side, you see that these are the trip purposes available in our household travel survey. And then we put each trip purpose into the category. So for example, for work trip category, we have trip purpose for work from home, work at non-home location, and work activity to drop off, pick up someone or something. And then for care trips category, we have trip purpose of attending child or adult care, dropping off, picking up someone, having healthcare visit, buying meals, shopping, buying or picking up goods, and doing other errands. And for leisure trips, we have volunteer activities, exercise, recreational activities, visiting others, rest, relaxation, vacation, or religious community activities. I would like to point out here that different studies could divide care trips differently. Like, for example, some previous studies put exercise as part of care activities. So every trip, every travel taken to exercise count as care trips, because the argument is like exercise is part of self-care. So that's how they define that as part of care trips. But in our study, it is important for me to also lay out this categorization to say that we don't count self-care as care trips in this study. Basically because some of the self-care, most self-care activities don't have similar characteristic with other care activities and their trips. Like, for example, with exercise or relaxation as part of self-care activities, men tend to take more trips for exercise and relaxation than women, which is more similar with other leisure trips. While in care trips, women tend to do more care trips than men. So in this case, because we see that they have for like self-care activities or trips to self-care activities have similar characteristic more to the leisure trips. So we put them into leisure trip category. So this is the results of our analysis. We found that care trips are significant. So how significant are care trips? We found that care trips make up the majority of trips people take. In the graph, you will see the descriptive statistics that we found from the data, that people tend to spend more time on care trips than work or leisure trips. And it is even more prominent among female or women. And you can see here that actually in the blue bar, which is the homebound trips, they have like a larger share than care trips. But I'd like to point out that homebound trips in our analysis are all returning trips from any other trip categories. Like, for example, you go to your work location, that counts as work trip, and then you go home, so that counts as home trips. And then you go to a grocery store, that counts as care trips, and then you go home, that counts as homebound trips. So basically, most like homebound trips mostly are the pair of returning trips from care, leisure, school, work, or other trips. So that's why we have a large share of home trips. I would also like to repeat that we would like to focus more on 3 main categories of trips, which are care, work, and leisure. And our descriptive statistics is also supported by what we found in our model. So here in the table, you will see the results of our modeling, MDCEV modeling. We do 2 kinds of models. The first one is we only take account only on the constants. So we don't put the sociodemographics factors there. And in model 2, we include the predictors. We include the sociodemographics as predictors. So from both models, we found that the care trips make up the majority of trips people take in their daily activities. It is seen by the lower coefficient estimates that care trips has in comparison with work and leisure trips. We note here that the baseline is non-travel activities, which is the most time-consuming alternative. And you see in the model 2, maybe you don't see the stars there. It shows that it isn't significant anymore because this is the constant. It's not significant anymore because we have included predictor. So the significance we can see later in the coefficient estimates of each predictors. So the significance of care trips is also showed clearly among employed people, because here in the graph you will see that even employed people make more care-related trips than work trips. And we also have done chi-square tests to see to establish this, that this is significance, the differences between trip type by employment status. And we found that care trips are significant even for employed people because they spend more time on care-related trips than work trips. Care trips are significant, especially for women, unemployed people, and those who live with children. So these are the results from the model 2, which we include the social demographic factors to the model. We see that people who are employed, they tend to spend less time on care trips. But people who don't work, like for example, looking for a job, homemaker, and then retirees, they tend to spend more time on care trips. We also found that household that has at least 1 child tend to spend more time on care trips, especially women who live in a household of multi-adults and at least 1 child. They tend to spend more time on care trips. So we found that, having said that, we can say that commute-centric transportation is at risk of neglecting care trips because people who engage more in care trips are less likely to engage in commute travel. We have women, unemployed people, and those who live with children. Even though we found that care trips spend a larger share of our time than work and leisure trips. And we also found from this study that employment status is an emerging factors defining time allocation on care trips. So previous studies mostly discuss about or focus on gender, but we also found that employment status has an important role in defining how people allocate their time to care trips. So to conclude my presentation, I would like to discuss the policy implication of our studies. So first, because we found that care trips are most likely to be done than work and leisure trips in terms of time allocation, we would like to suggest that travel demand modeling to consider care-related places in trip generation and trip attraction. And because we leverage the use of household travel survey, it will be like a huge improvement for household travel survey if care trips are included in on the trip purpose categorization in travel survey. And from our second finding that women unemployed and those living with children are more likely to engage in care trips, we will suggest to have public transit operation that can be more care supportive. Like, for example, having open stroller policy. Open stroller policy is like the agency allow passengers to board their stroller without having to hold it. It is really helpful for women who travel with children, because they will like attending their child, they have their stroller, and then they have, let's say, the grocery bags, and how to manage that if they have to like close their stroller and then board to the bus and or train. It will be a little bit burdensome. So it will be really helpful to have a care supportive public transit operation by their policy, like open stroller policy, youth-free fare, and free transfer. And also, I would like to also highlight the benefit to have a mixed-use land development. So it will ease the burden of having doing care trips, because with mixed-use land development, we will hope for increasing access to care-related destination, and it will help minimize travel time while chaining from one care activity to another care activities in care trips chain. So that's all from me today. Thank you so much for your attention. I'm happy to take any question. Thank you.
Okay, Naomi, thanks for the inspiring talk. Is there any question from the audience? If not, I'm wondering, so when you look at the significance of different type of trips, have you looked at the trip distance? For instance, the care trips often is shorter in distance compared to commute trips. Yeah.
Okay, in this study, we didn't take a look specifically on trip distance, but I did take a look at that too when looking at the descriptive statistics that care trips tend to happen in shorter distance. But in this analysis too, we with purpose in purpose like narrowing down control the trips that is short distance. So actually care trips can be happen in long distance too, like let's say you taking care of your elderly parents in other state, so you have to like fly there, but we exclude that trips. So we like in purpose focus on shorter like short distance trips, care trips.
Okay. Thanks very much. So if there's no further questions, so let's thank the speaker again, and we will move on to the next talk. Okay, so the third talk will be given by Jiaqing Lu from the Florida State University, in the research group led by Professor Qianwen Guo. Okay, so Jiaqing, the floor is yours.
Good afternoon, everyone. My name is Jiaqing Lu, a PhD candidate from the Florida State University. And today I will be presenting our research titled Equity-Aware Design and Timing of Fare-Free Transit Zoning under Demand Uncertainty. This research is supervised by my professor, Dr. Qianwen Guo from the Florida State University, and Dr. Josie Cho from the New York University, and Dr. Po Field from the University of Maryland. So let's begin in my presentation. And at the beginning, let's navigate through the structure of my presentation. I will illustrate our research through the background, motivation, and the model setup, results, and get some the conclusion. So let me introduce some the background for our research. So transit systems are important for providing mobility, especially to underserved populations. However, traditional fare structures often create barriers to access. Fare-free transit have been shown to improve equity by reducing these barriers, but their design and implementation need to take account for demand uncertainty in the like the ridership or the auto demand in the corridor. So if not carefully planned, such policy may strain system resources or fail to serve the populations that need them most. So our study explores how fare-free transit zones can be designed and implemented to address equity while responding to the fluctuating transit demand. I will use Utah Transit Fare-Free Zone and UT Blue Line as an example to illustrate uh, our research result. So for the fare-free transit policy, the concept dates back to the 1960s, starting with an experiment in the Belgium. Throughout the 1980s and 1990s, several small cities adopted fare-free transit on a limited scale. More recently, larger regions have embraced it, such as France, which made buses and trains free in 2018, and Luxembourg, which became the first country to offer the nationwide fare-free public transportation in the 2020. However, the COVID-19 pandemic significantly impacts this free policy, with some agencies discontinuing fare-free transit due to reduced transit ridership. The figure shows the map of the all fare-free program in US during COVID-19. In some, nearly 60% agencies were found to have suspended fare collection in their transit system. However, some the transit agencies still provide free fares to enable people experiencing homelessness to travel on their system. Fare-free transit continue to be a topic of discussion and debate among policymakers, transportation experts, and communities in the post-COVID-19 era. So for this policies, it has some benefit and challenges. It promises better accessibility and operational savings, but challenges like the increased ridership and lost farebox revenue make it a complex policy decision for implementing this policy in their transit system. Most previous studies focus on the Small systems are our special communities like the school bus or some free bus in the near the uh, near the beach community, and also they just did some static cost benefit analysis for this topic. So there are some of the key gaps like limited attention to the equity impact and also these studies didn't address when and where the fare-free service should be implemented or withdraw in their transit system. So our research is to propose a dynamic model to determine both the timing and strategy for implementing fare-free transit from the two perspectives, social welfare and social equity. So let's see some the model setup. So from the beginning, the potential travel demand is assumed by the linear function in a traffic corridor. It is decreased from the CBD to the city boundary. So the user cost for the bus and auto, the bus user cost included the in-vehicle travel time, waiting time, and fare and access time. So we transfer the time to the money with some coefficient in the equation. And for the auto users, they need to spend like the fixed cost, like parking charge in the CBD per work trip, and some the variable cost like auto gas price per unit distance. And they also need to spend the travel time in this process, and then we use a coefficient to transfer the time to the money in the equation, so we can get the user cost for the auto and the bus. And then we need to get the travel demand density by bus over the auto at location X. So we use a logic model to separate the demand for the bus and auto. This model use their cost to separate demand in this location, so we can get travel demand density for the different mode in at location X. And then we need to get the actual demand because the passenger or the traveler choose their travel mode according to the costs they need to spend on the road. So this is a elastic process. So we use this equation to get the actual demand density at location X according the cost at location X and the coefficient. So we can get the social welfare after we get the actual demand and the cost, the user cost for the bus mode, auto, and the bus. For the social welfare, we have the two choice, fare-based transit service and fare-free transit service. The difference between them is because each component is different. So they included the user surplus fare revenue and operation cost and fare collection cost. And for the fare-free transit service, we also need to take count of the administrative cost of the fare-free transit. So for the each user surplus, it can be computed by integrating the inverted function over the actual demand. This is a traditional method proposed by the Chang and Songfield. So another component we need take account is social equity. For the social equity, we separate the demand along the traffic corridor to the demand group, which is distributed along the corridor. So we use a Gini index to define the inequality ratios of the user supplies. Then after we get the social welfare for the different trend service, fare-based trend service and fare-free trend service, we use a dynamic model to switching between these two services. So as we know, the travel demand density is uncertainty or our unpredictability in our real life. So we use geometric Brown motion to stimulate the travel demand density along the corridor. So we simulate the demand according to the historical date from some transient agent, our transient system. And then after we get demand, we develop the stochastic switching model with a market entry and exit real option approach. By using this approach, we extended the statics model to the dynamic model to find the optimal switching timing between these two service modes. So this approach is a decision-making tool that is particularly useful in the analyzing switching problem in dynamic and uncertainty environments. So the problem of the stochastic switching between the fare-based and the fare-free transient is addressed using the asset equilibrium pricing of the real option approach, which involves building the differential equations for the dynamic equilibrium value of the switching based on a stochastic process. Specifically, we establish equation for the equilibrium values of the fare-based transient service and the fare-free transient service based on the threshold between the two models. The omega Q is the difference between the social welfare of these two service mode. We calculate this difference. We calculate this difference according to the social welfare we get in the previous slide. In order to switch from one service to another, the threshold is not a single one because switching costs exist. Instead, switching costs lead to the two switching threshold, which we consider as the demand threshold QH and QL. To follow the value matching equations, we get the option values of these two thresholds. Through the smoothing testing, we get other two equations. Then we can obtain the QH and the QL through the solving these four equations. So the QL is switching from the fare-free transient service to fare-based transient service, and QH is switching from the fare-based transit service to fare-free transit service. So let's see some the result, see some the our research results. So from the perspective of the social welfare, we optimize the transit frequency and the length of the fare-free transit service with the objective of the maximizing social welfare. We get the within the 50 miles traffic corridors, we get 32 miles for the fare-free transit service and 13 bus per hour for the transit frequency is this is a optimized result for the statics model. And we can see the model split within the fare-free transit zones. The bus ridership or bus demand is increased compared to the ridership outside the fare-free transit zone, and the auto is reversed compared to the bus demand. And from the perspective of the social equity, we find that as the fare decrease and the fare-free zone length increases, the Gini index declines, meaning reduce inequity among users that improve the social equity. And we also use Lorentz curves to visualize the different transit service policy. From the result, we found that full fare free transit. That means in the whole corridors, the transit systems is implemented by the fare free policy. So it is show that highest equity in the whole systems. And for the dynamic models, we use a case study to show our model to show the benefit of our model, and we use UT blue light rail corridor in the Salt Lake City. In the Salt Lake City, they have the fare free zone in the downtown area, so it is a good example to apply our models and find some result. So for to optimize the length of the fare free transit, in the case study we use the two objective oriented, like the equity readme and welfare readme. This is the two oriented. One is we just consider the social equity, so we can get the optimized length for the fare free transit is a full corridor for this system. But if we just consider the social welfare, we can get optimize the length for the fare free transit is about 15 over the 18 miles corridor. And to get the for these two oriented policies, we can get two different we can get a different switching timing for if we consider the different objectives. Like firstly we can get a switching threshold with dynamic demand and with the simulated demand trajectories, we get the service activation and cancellation timing for these systems. For these systems, when we consider the different objectives, this is different, and so this table shows that how they are different, and we can say that for the EQT region, which use a full length fare-free coverage, transient, and for the welfare regime, which use optimized about 16 miles fare-free zones. So the welfare the regime shows both earlier start and later termination of the fare-free service. And the numbers of the implementation period remains constant for these two regimes. The total fare-free duration is longer under the welfare regime, which improve the service stability. When switching costs are excluded, fewer switches are needed, reducing the operational description and improving the adaptability. Overall, this strategic alternation based on the demand density enables more cost-efficient, effective, and responsive transit planning. So we get some conclusions from our research that fare-free zones directly stimulate transit demand. However, it also highlights a potential drawback, like the outside the zones user shift toward private car use, which could counteract broader transit goals. And secondly, as the fare-free area expanded, more riders within the fare-free zone choose choose both bus and auto modes, and thirdly, fire elimination improves the equity by making the transit more accessible to the disadvantaged groups. The Lawrence curves and the Gini index both show that full fare-free implementation along the whole transit traffic corridor achieves the best equity outcomes across on all demand groups. And fourthly, when optimizing for the both social welfare and equity, the fare-free zones become the longer. This is important because it suggests that the policy goals need to balance total benefit with a fair distribution, and that equity often requires more genius service design. And finally, our dynamic model, especially under the welfare regime, allows for the earlier and longer fare-free service implementation. This flexibility is important and crucial under the uncertainty travel demand, and it emphasizes the value of the using real options modeling to make adaptive and cost effective decisions for our transit system. Yeah, that's all. This is our research, and thank you for your listening.
Okay, thanks very much for your interesting talk. So given that we're running out of time, so I will leave the Q&A session to the offline. Okay, so if you're interested, you can raise questions to the author directly. Let's move to the next speaker directly. The next speaker will be Priyanka Paifanka from the University of Texas. Please go ahead.
Okay. Hello, everyone. I'm Priyanka. Let me just remove this Zoom. Okay. Let's continue. I'm a PhD student at UT Austin. I'm advised by Dr. Kara Kockelman. My research focus is on demand, fare, and fleet analysis for on-demand autonomous mobility service. And today I'll be talking about fare and demand interactions in a duopolistic TNC market. So we all know that ride-hailing demand varies significantly across space and time due to various rider preferences and neighborhood factors. And companies use these time and location-based fare adjustment, which we all are familiar with. It's called surge pricing. It affects both passenger demand and vehicle dispatch strategies. So the past research, while they study surging effects, often overlook the feedback loop between fare changes and the number of people requesting the rides, and also vice versa. So even the daily and weekly demand cycles are well studied, they lack focus on these looping effects. So this study jointly models this interaction between Uber and Lyft fares with total trip count using simultaneous linear system of instruments. So the past literature roughly divides into 8 categories. We have some studies looking into agent-based modeling. It analyzes the competition among different transportation modes, such as public transit versus TNCs, and they focus on economic competitiveness by testing different fare strategies. On supply side, there are several who have examined whether the new mobility service will be substitute or will supplement to existing transportation option. And then the few have looked into differentiated service offerings. On demand side, there is a substantial research. It has been done in understanding the rider preferences based on cost, convenience, and service quality. And if you have looked into market equilibrium by estimating ride-hailing fares and destination together. And there is other body of research who focused on change in regulations, market concentration, and policy changes on these posted fares and its effect on TNC competition. So this study extends this research by modeling operator-specific fare using 2 dominant operators, Uber and Lyft, while accounting for spatial and temporal spillovers, and also the endogeneity between the fare and demand, using 3-stage simultaneous equation. And we will look into how fare strategies vary across operators, neighborhoods, and time of the day. So for this, we are using New York's taxi and limousine licensed FHV database. We collected 9.8 million pickups and drop-offs from September 15th to 30th, 2024. And these trips cover around 65 to 70% for higher trips, which are served by just Uber and Lyft alone. And the rest market is served by yellow taxis. So the data shows that highest pickups were recorded from Manhattan, which is 41% of the total data, followed by Brooklyn and Queens, and then Bronx, and then Staten Island. We also see no pickups at Newark Airport, but there are drop-offs recorded at Newark Airport, which is 69,000, because it's not part of New York City, but there are trips who originated in the city and ended at the airport location. So that is reflected on the drop-off figure here. So if we just compare the taxi zones, we can see that highest trip activity is at LaGuardia and JFK airports. They make up 3.8% of total pickups and 4.5% of total drop-offs. If we look at the temporal distribution of these pickups per day over 24 hours, we can see two clear peaks on weekdays. So we have one in the morning, 7 to 9 a.m., and then one in the evening, 4 to 7 p.m., which likely shows commute trips. We have highest pickups on Friday, 8 a.m. in the morning, and then 6 to 7 p.m. in the evening. And as the weekend arrives, we have leisure travel dominating in the network. We see a sustained midday trips gradually increasing towards late evening and even during midnight on Saturdays and Sundays. Interestingly, leisure after-hours activities keep demand up even during the early mornings of weekend too. If you look at the statistics, Uber dominates in this New York market. They serve around 72% of the trips. 3% of these were pooling requests, but just 0.9% were matched. And 41% of these trips paid 2.7 congestion surcharge, which means that these rides either began, ended, or passed through Manhattan's south of 96th Street. 24% of these trips passed through new congestion zone, which is south of 68th Street, and they will be now subjected to additional $1.5 per trip as part of New York's congestion pricing program, which was launched in January 5, 2025. In addition to these, riders pay $2.5 for airport travel, 8.9% of sales tax, 2.75% of Black Car Fund, which it supports driver benefits and safety programs. So this figure shows average fare per mile distribution across hours and days. And we see that fares peaking on Wednesdays and Thursdays. It crosses around $7 per hour during evening rush hours. Weekend fare variations are quite moderate compared to weekdays. And then we see a gradual increase until early evening. Interestingly, Lyft consistently offers lower fares on Mondays and Sundays, but that's not the case on Thursday and Wednesdays. So to get the demographic information of these taxi zones, we have used EPS smart location data, and then we spatially joined the taxi zones with census tracts. The meteorological data was obtained from Meteostat, collected at Manhattan's weather station. It includes average precipitation, temperature, and wind speed. And then to capture this short-term demand and fare variations, these trips were grouped into 10-minute beans in each taxi zone. And these 9.8 million trips were distributed into 495,000 zone time bins, so which theoretically is over 560,000 zone bins, but just 495,000 bins had non-zero trips. And then we summed trip counts and averaged all the fares in this spatiotemporal cluster, where this cluster, where errors in this cluster vary across space, across taxi zone, and then time, so across this 10-minute bins. So in this competitive market, we know that demand is influenced by fares, and then fares are adjusting in response to the demand. So this simultaneity creates endogeneity, and it cannot be addressed by OLS alone. So to resolve this feedback correlation, instrumental variables are also used. So we use daily precipitation, temperature, and wind speed as instrument, which affects demand, but do not directly influence the fare settings. So we can see that the demand equation are total number of trips in pickup zone at that time interval, influenced by passenger wait times, fares, socioeconomic characteristics, and weather condition. And then the fare equation models average fare per mile for that zone 10-minute bin. In addition to these, we used event-specific shocks. For example, conferences, festivals in the New York City that can temporarily affect these, both of these demand and fare. So these events are UN's General Assembly, which happened between September 19th to 23, Climate Week from September 17th to 24th, and then Global Citizen Festival on September 23rd. And then errors are clustered by combined identifier with zone I and time binting. We used a cluster robust estimator that accounts for correlation within the error cluster. So if we assume that WIT, VIT, and UIT are unobserved error terms in demand, Uber fare, and Lyft fare, then we get the error vector EIT. And this error vector follows a multivariate distribution with all possible correlation across equations. And the covariance matrix includes diagonal elements, which are variance of errors for each equation, which is demand and Uber fare and Lyft fare. And then off-diagonal elements capture the covariance across equations. So for example, sigma du will measure how unexpected changes in demand may be related to unexpected changes in Uber fare. But this robust estimator only addresses correlation within the cluster. It cannot address correlation across clusters. So we used multi-way bootstrap method where we generate distribution of parameters by resampling this cluster with replacement. So for each bootstrap iteration, we will sample the cluster separately across time and then zones. And then for this one bootstrap sample, we will include only those observations whose zonal and time pairs falls into the bootstrap iteration. And for these observation, we will estimate the three-stage simultaneous equation, and we get a new set of parameters for each of this replication. And for this study, we have used 2000 replication. So we have got a distribution of bootstrap estimates for each model, which captures the variability in parameters due to cross-cluster dependencies. So these are the demand equation estimates. So we see intuitively that as the fares go up, it reduces the demand. So if ride-hailing fares go up, fewer people will use this service. So Lyft riders were seen far more price sensitive than cost-conscious Uber riders. We also see the effect of longer wait times. It discourages riders to make any TNC trip. We saw that neighborhood characteristics also affecting the demand. So the trip count increases in high residential density and also with more workers per job available in taxi zone. Interestingly, single, divorced, and widowed individuals have seen to increase the demand, likely due to their personal need of mobility option. And in the other hand, married people can coordinate their travel and they can rely more on household vehicles, so they are seen to be reducing the ride-hailing demand. To quantify these sensitivities, we looked at the change in predicted Y, which is demand, in this case, after increasing each X by its own standard deviation. And we found that when Uber's fare rises by its own standard deviation, it causes 27% reduction in demand, and the similar rise in Lyft's fare causes 90% reduction in demand. To normalize these effects, we increased the fares by $1 per mile, which caused, so this increase in Uber's fare caused 5.8% decrease in demand for Uber, but over 60% for Lyft. We also see that rise in wait time just by 1.54 minute caused 37% reduction in demand, which shows that riders are quite sensitive to these delays. Married residents showed 10% reduction in demand, while widowed separated families increased it by 3.7 and 4.4%. Residential density also influenced demand. One standard deviation rise, see around 3.6% increase in ride-hailing usage. Now, if you look at the fare side, both platforms implement surge pricing, raising fares as demand goes up, and we see that Uber way more aggressive than Lyft. We also see that as the fare goes up, with passenger wait times, which means with the increase in passenger wait times, the supply is going down. So platforms are raising their fares to attract more drivers in that area. And we see that Lyft's ridership is more sensitive to delays than this Uber's. Education and earnings also affect the fares. We see lower income worker neighborhoods have higher fares, and high income neighborhoods have low fares, which seem to be counterintuitive, but this is likely due to often drivers try to position themselves in safe, lucrative areas or the timings when the high tipping potential arrives. So we often, this kind of time and zonal area, it correlates with high income neighborhoods. So driver supply is more in such areas, which keeps the fares down. Climate Week and Global Citizen Festival also contributed to this short-term spike in fares. So to sum up, this study, we tried to address the simultaneity between operator-specific fares and demand, considering errors across space and time. On fare side, we found that Lyft riders are being much more sensitive than Uber's, where $1 per mile increase caused 5.8% reduction in Uber's demand, but over 60% in Lyft's demand. While on demand side, Uber's fare, on fare side, Uber's fare were more responsive to demand than Lyft. So a standard deviation rise in trip count increases the Uber's fare by 9%, but it only increases 2.2% in case of Lyft. When wait time increases, surge pricing pushes fares even higher to attract more drivers in that area. But even the small increase in wait time, for example, 1.54 minutes, leads to significant drop in demand. We also see that New York's market is highly sensitive to everyday weather shifts. People avoid going out in bad weather. So unless it absolutely is necessary, as we see that one standard deviation increase in precipitation causes 17% drop in demand. On the other hand, city is quite active on warm and breezy days. So we see a small uptick in rides as the temperature goes up. Okay, so the future direction for this study will be to also incorporate the driver side of effects, which is acceptance rate, and also to include the fleet size, which is on the supply side. The model can be also further refined by exploring the rider side of factors, where the brand loyalty and the past wait time experience significantly affects the choice of the operator. Also investigating the various service options, for example, Uber XL versus Lyft Line, will further we will be able to zoom into the differentiated effects. And since this data was for just 15 days in a September time period, it cannot capture seasonal and annual variation. So extending the time frame will definitely improve this model. Thank you for listening, and I'll happy to take any questions, suggestions you may have.
Okay, thanks for interesting talk. Is there any question from the audience? Okay, so if not, I have a very quick question. I'm wondering, in the data set from New York City, how do you obtain the passenger waiting time? Because as far as I recall, that data is not available in that data set.
We can calculate passenger wait time. So we do have a time when the request was made and the time when the vehicle arrived to pick up the request.
Oh, you have that. Okay, I see. I see.
Yes.
Okay, then that's fine. Okay. Thanks very much. And then let's move to the last speaker. The last speaker is Mira Dibab from Aalto University. So please go ahead. The floor is yours.
Hello, everyone. My name is Samira Dibaj. I am a doctoral candidate at Aalto University in Finland. Together with my colleagues in University of Tsukuba and my supervisor, I am presenting this study about understanding those who are not using e-scooters. So the specific characteristics of e-scooters, and this is a comparative latent class study comparing Helsinki and Tokyo. In this presentation, first I'm going to present a brief introduction about shared e-scooter emergence, and then the research aim is going to be emphasized. Then we are going to go to methodology, and in the methodology section, I'm going to explain the case studies and the data collection method that we had, and finally move on to the model. Then the model results and the conclusion is going to be presented. As we all we know, the emergence of e-micromobility all over the world has gained some popularities, and these popularities are mostly for the users of these systems. For example, the users are using e-scooters to have fun, to increase their speed, or because it is very much accessible almost everywhere in different locations, and also for complementing the first mile and last mile of their public transport trips. However, on the other hand, there are non-users. They are, of course, the majority of people in the city who have never tried e-scooters in their life, and they often bear the negative consequences of e-scooter deployment in the city. We want to focus on the non-users in this study, because most of the studies so far have been done on the characteristics of e-scooter users and what they think about these systems. But we believe that the non-users are also an ununiform group of non-users, and they are very much less focused in the scooter-related studies and the literature. Therefore, the aim of this study is to understand the heterogeneity among non-users and their perspectives toward e-scooters, to understand their reasons why they are not using these systems. According to the previous literature on e-scooter non-users, completely like on the other hand of e-scooter users, the e-scooter non-users are mostly female, and they are older than 25 years old. The reasons that they don't use e-scooter is that they find it unnecessary to use, and also they believe that using the scooters can cause some safety-related problems and concerns. They believe that the condition of the road is a bit poor, and also sometimes some groups believe that the e-scooters are very pricey to rent, and also they simply don't know how to use it. And the non-users also have some recommendations to improve this system. According to the literature, they recommend to the e-scooter users to follow the traffic regulations and not use the sidewalks for riding the e-scooters, and also have a responsible parkings. Some other groups of these e-scooter non-users also are a bit more strict, and they suggest some kind of penalty and fines for the e-scooter users who are not following the traffic rules. And the non-users usually and mostly have negative perspectives towards e-scooters, because of the media and what they see in the streets. They believe that they are causing injuries, very much unsustainable mode of transportation because they believe that it is mostly substituting walking and cycling. This study addresses the gap in the literature by examining non-user classification in cities outside the US, because most of the literature is focused on the US-based cities. So in this study, we employed a comparative case study of Helsinki in Finland and 3 wards in Tokyo, Japan, naming Shibuya, Meguro, and Minato. They have been selected because they have similar population size compared to Helsinki, and the e-scooter service exists in these wards, and also because of the comparable governance approaches that these 2 cities have. So in Helsinki, when the shared e-scooter emerged in Helsinki about late 2018, but in Tokyo it emerged a bit later. It was mostly late 2020. At the time of our data collection, which was in 2022, there were 5 shared e-scooter operators in Helsinki, whereas in Tokyo there were 8 shared e-scooter operators, and out of these 8 shared e-scooter operators, only one of them was like distributed all over Tokyo. And online questionnaire in Helsinki was distributed during summer in 21 days, and it ended up with 7,700 respondents. And after cleaning the data, putting aside the e-scooter users, we ended up with around 2,000 e-scooter non-users. Whereas the exact same questionnaire was used in Tokyo in November 2022, and during 6 days of this response collection that was done mostly by a survey company, they gathered 1,500 respondents, and out of that they had 1,225 e-scooter non-users. So you can see that mostly out of their questionnaire, like the majority of the respondents were non-users. Yeah. So moving on to the next slide. The sample characteristics here in this table shows that the gender distribution in both samples closely matched the general population of the city of Helsinki and Tokyo. In Helsinki, women make up around 52% of the population compared to 45.5% in the sample. While in Tokyo, the female population is 52.5, and in the sample, it is almost similar. The results of the sample is very much representative in Tokyo's case compared to Finland's case, because the survey collection in Tokyo was done by a survey company, and they tried to have this representative of the population. But in Helsinki, it was done through distributing the questionnaire in social media, and also distributing the questionnaire in the e-scooter operators' applications. In both of these cities, you can see that the non-users are mostly female. And Tokyo has a higher proportion of non-users under 24 years old and over 54 years old compared to Helsinki. And also the income level is kind of different in these 2 cases. Employment trend shows that most non-users in both cities are employed, but Tokyo has over 3 times more the population of unemployment of non-users compared to Helsinki. Other questions that were asked in the questionnaire were some awareness about the e-scooter issues in the city, such as how much they are aware of these problems, such as riding the scooter in the sidewalks or improper parking behavior, not keeping a safe distance while riding e-scooters, and so on. We also asked about the reasons that the person is not willing to use or has not ever used e-scooter. For example, they could choose between these options. They might find it unnecessary to use, or they might believe that e-scooters are very unsafe to use, or they believe that it is a pricey mode and it's expensive mode, or other options. For example, this person has low competence to ride an e-scooter. Maybe they don't feel confident enough to ride these e-scooters. And some other practical reasons, such as not having a smartphone or bank account, and so on. Another set of questions that were asked were suggested improvements regarding e-scooter usage. For example, we asked, what do you suggest for like to improve the shared e-scooter deployment and usage in your city? And they were able to choose between these options, such as the improving the streets infrastructure, or improving the rules of riding, or improving the parking behavior, and so on. So all of these questions were used in they were used to create latent classes of non-users. We employed this latent class analysis because we wanted to identify latent groups among e-scooter non-users who had similar combination of socio-demographic characteristics, reasons for not using e-scooter, perspectives on e-scooter riding practices, and awareness of associated issues. This LCA works in a way that it assigns a conditional probability of belonging to one latent class over the other latent class for each individual. So based on in our model, we used all of these parameters and variables that I already mentioned. So socio-demographic characteristics were involved, reasons for not using e-scooters, perspectives on e-scooter riding practices, and awareness of these of specific riding issues in the city. Based on our model results that we did in Stata, based on the lowest value of AIC and BIC, as you can see in this table, along with the fact that we wanted to maintain the same number of classes for Helsinki and Tokyo for the purpose of comparability, 5 number of latent classes were selected for further clustering. This is the outcome of our model that I tried to summarize in a way to be easy to understand. So we during our analysis we realized that most of the non-users are they have very much negative perspectives towards e-scooters. So we decided to sort these non-user groups in this order of having the most negative perspectives, with showing with warmer color, with the red color in the left-hand side, moving towards the right hand of this graph as the color is more yellowish, to people who had the least negative perspectives. And these numbers that you can see in the middle, they show the size of each of these classes. And you can see that, for example, class 1 and 3, they almost have the similar size. But I want to go one by one into each of these classes to explain the characteristics of these classes. For example, class 1 mostly belongs to female. I mean, the number of female in this group is very high, and they age like almost middle age, like young to middle age, 35 to 64. Their income level is high or moderately high comparing to different cities and our case studies. They are employed and they are very much educated, and they have very high cycling experience. This group of non-user has the most negative perspective towards e-scooters. They believe that e-scooters are not necessary to be used, and they can cause a lot of issues in the cities, and they shouldn't even be used in the cities. They should be banned. They have very strong negative perspective towards e-scooters. Moving on to the next group, it is again mostly contains of female, but they are a bit younger in Helsinki, but a bit older in Tokyo. And this group is very like they are employed mostly and have high educational level and higher cycling experience. But the important difference between these two is that the reason for not using e-scooters for them is mostly safety concerns. This group is more concerned about the safety of e-scooters, and based on our analysis, we realize that most of these people, these women, are mothers and they have children, and they are very much concerned about their like these vehicles around their children. The third class mostly belongs to older people, and they have a bit less income. But as maybe a lot of us would assume that most of the non-users who have negative perspectives towards e-scooter would be older people, adults. This group is not that much, and they have like moderate negative perspective toward e-scooter, not as much as the first two groups. The fourth group mostly belongs to mostly to lower income groups, to students or to people who are unemployed or on leave. And the percentage of this class in Tokyo is very, very higher than Helsinki, almost 4 times higher. It shows that in Tokyo, where the shared e-scooter emerged later than Helsinki, people, mostly students and lower income groups, are very much interested in using e-scooters. But the reason for not using it is mostly because of the price of these vehicles and renting these vehicles. So if the price was a bit moderated, maybe they were more willing to use shared e-scooters. So the fifth class is very much different in Helsinki compared to Tokyo. In Helsinki, they are those group of people who are again female, but the number of female in this group is very less than compared to other 4 classes. So number of males is almost the same as female in this group. They are very they have the highest income, very like employed, and a good cycling experience. But the reasons for them to not use e-scooter is that they don't feel confident to use these scooters. Maybe they don't know how to use it, or the e-scooters are not available in their areas, or they have other reasons for not using e-scooters. But in Tokyo, this last class is very much indifferent about e-scooters. Some of them they even didn't know that e-scooter exist in urban mobility. So the lack of awareness about e-scooters are shown in last class in Tokyo. So that was the result of our model. The conclusion in our research First of all, we investigated the e-scooter non-user profiles and preferences using latent class analysis in Helsinki and Tokyo. We concluded that e-scooter non-users span from having very negative perspective towards the least negative perspective, and even people who are not even aware of these vehicles in the city, and they are very indifferent about them. The group of people who have the most negative perspectives towards e-scooter are usually female, who are very high experienced cyclists, and they are middle-aged, employed with high income, and their most concern about e-scooters is the safety and the fact that they believe that they are unnecessary in their urban mobility. Whereas the last two classes, class 4 and class 5, could be the possible future e-scooter users. The fourth class was belonging to lower income group, mostly students who maybe want to use e-scooters, but they can't use it because of its price. And the class 5 in Helsinki was belonging to group of again high income middle-aged people who didn't use e-scooter because of the practical reasons that they had, such as not having e-scooters available to them in their original destination, or not having other necessary materials to use e-scooters. And the class 5 in Tokyo, they were again having almost the same characteristics, but with the lowest cycling experience among all the other groups. And this group was very much unaware of e-scooters in the city. So increasing the awareness about other modes that could be available for them could kind of move them towards trying other modes of transportation. This clustering approach help us to provide, it can help us to provide personalized e-scooter usage packages for non-users. Mostly this can be used by the e-scooter operators and the companies to include and to invite other people who are the non-users to try their vehicles. And it can improve the effectiveness of e-scooter usage for the company. Thank you very much.
Okay, thanks for the very inspiring talk. So is there any question from the audience?
Hi, Dr. Lee. Hi, Summer. I have a question. So, for the questionnaires, this is you conduct the questionnaire is have the reward for the participant, or it is a volunteer survey?
Yes, thank you very much for the question. Well, we had, let's say, a draw that we had 20 gift cards to give out at the end of the questionnaire. It was a random draw. So people who wanted to be included in this like a lottery kind of a thing, they needed to enter their email address, and we did the random draw and gave away the gift cards for them.
Very cool. So, this for the participant is a random, or is some oriented group like student, or
Yes.
you in a student for the
No, it wasn't students. In Tokyo, it was distributed by a survey company. So they tried to completely represent the population. That's why the number of older adults and also people who are less than 24 years old is higher compared to Helsinki in Tokyo. But in Helsinki, we distributed the questionnaire through social media, such as LinkedIn, and also through the website of City of Helsinki, And we also used, I mean, some shared e-scooter operators helped us to like distribute the questionnaire through their applications. So in Helsinki, the reason that we received a lot of respondents and we had also a lot of e-scooter users that data was used in other papers. The reason for that is that we used different channels for distributing the questionnaire, but we sacrificed some representativeness of the data in this way.
I got. Thank you. Thank you,
you.
answer.
Okay, so thanks for the discussion, and we are a bit over time, so we'll stop here, and this session will be concluded. Thanks again for presenting and attending. Okay, that's all for today.